Hey friends, let's dive into something mind-bending today. Take a close look at a Möbius strip. Go ahead, picture it in your mind, or grab one if you have it. Now honestly tell me in the comments, how many sides does it have? Most of you might say 2, right? But here's the kicker. The Möbius strip has only one side. Don't believe me? Let me prove it. Imagine drawing a line along one side of the Möbius strip, starting at any point and continuing until you return to where you began. You'll notice something wild. The line covers both surfaces without ever lifting your pen. This shows the Möbius strip is a single-sided object. What looks like 2 sides is just an illusion created by its twisted geometry. Now, let's shift gears to another illusion: mirrors. Place 2 mirrors facing each other, and you'll see what appears to be an infinite number of reflections. But are there really infinite mirrors or lights inside? Of course not. It's just light bouncing back and forth, creating the appearance of infinity. In fact, there is a simple formula to calculate the number of reflections based on the angle between the mirrors. If the mirrors are parallel, the 60-degree angle, the formula gives us 360, which seems to suggest infinity. But here's the catch. Division by 0 isn't infinity. It's undefined. This is a common misconception taught in schools, but mathematically, 1 over 0 doesn't yield a single answer like infinity. It could be anything: 5, 17, a million, or even undefined, because no real number satisfies the equation in 0 x 1. This brings us to a profound question. If our universe appears infinite, like the reflections in those mirrors, is it truly boundless, or is it, like the Möbius strip, a finite object disguised as something infinite? Now, let's shift our focus to the intriguing possibility that our universe could be finite but unbounded. Picture this: a vast expanse stretching out before you, seemingly endless. But what if after an eternity of wandering, you find yourself back where you started? Welcome to the mind-bending realm of the torus, a shape that defies conventional notions of infinity. Historically, things we once thought were infinite turned out to be finite. For example, Galileo believed light's speed was infinite, but we now know it's a finite 299,792,458 meters per second, roughly 3 kilometers 108 meters. So, can we apply the same logic to define the universe's boundaries? To tackle this, let's revisit a famous paradox from 400 BCE by the Greek philosopher Zeno. He posed a thought experiment. To walk from your house to a park, you must first cover half the distance, then half of the remaining distance, then half of that, and so on. Each step is finite, but the number of steps seems infinite, suggesting you'd need infinite time to reach the park. Yet, in reality, you do reach the park? How? Mathematically, this is a converging series. If the total distance is d, you travel d to 2 plus d to 4 plus d 8 plus. This series sums to exactly d, a finite value, because the terms get smaller and converge to a limit. Now, apply this to the universe. If the universe were contracting, like in a hypothetical Big Crunch, its boundaries might converge, making it easier to visualize as finite. But our universe is expanding, behaving like a diverging series where distances grow larger. Does this mean it's infinite? Not necessarily. Let's consider a massive number to put things in perspective. The googol, 10 to 100. Introduced by mathematician Edward Kastner, a googol is larger than the estimated number of atoms in the observable universe, about 1080. Even if each atom contains roughly 1,000 subatomic particles, the total particle count is still far less than a googol. But here's the twist. The observable universe is just a fraction of the whole. Beyond what we can see, the universe could be vastly larger, or even finite but unbounded, like a sphere or a donut-shaped torus. Scientists have explored this using cosmological models based on the Big Bang and the cosmic microwave background, CMB. Data from the Planck Observatory suggests the universe S geometry might be station, might be flat, infinite, or slightly curved, finite, like a sphere or saddle. Let's talk about infinity. You might think of it as a never-ending series of numbers, like 1, 2, 3, going on forever. But did you know there's actually more than one kind of infinity? George Cantor, a brilliant mathematician, discovered different infinities. Here's the crazy part. One infinity is actually bigger than the other. Wait, how can infinite be bigger than infinite? It sounds impossible, but trust me, it's true. Let me explain. Check out these two sets of numbers. Set 1 includes all natural numbers, 1, 2, 3, and so on. And set 2 has all the even numbers, 2, 4, 6, and so on. Which set has more numbers? You might think they have the same amount since both are infinite. But here's the surprising part. Set 2 actually has fewer numbers than set 1. How can infinite be smaller than infinite? Here's the deal. Set 1 includes all natural numbers, while set 2 only has even numbers, which are basically a subset of the natural numbers. Cantor realized that different infinities can have different sizes. He named the infinity of natural numbers countably infinite, and it's the smaller of the two. The continuum infinity, on the other hand, is the infinite set of real numbers like pi and point. And Cantor proved that one infinity is actually bigger than the other. This blew people's minds because it challenged the idea that infinite is just a single concept. In fact, Cantor wondered if there are even more infinities between those two. His work opened up a whole new area of mathematics called generalized infinity. What's mind-boggling is that this infinite within infinite stuff is happening all around us. Consider the quantum world. Particles can be in multiple places at once. It's like they're in an infinite number of states until you measure them. But when you look, you only see one outcome. Where did the other infinities go? And is there a bigger infinity beyond the ones we know? These questions lead us to the edge of current mathematical understanding. It's a reminder that the universe never ceases to amaze, and there's always more to discover. In the early 1990s, a physicist named Paul Steinhardt proposed a radical idea that could redefine our understanding of the universe and potentially answer some of the deepest questions humanity has pondered for centuries. His idea revolved around the concept of a cellular cosmos, a universe composed of tiny cells with a diameter of about 1 millimeter. These cells would be the fundamental building blocks of reality, much like atoms are the basic constituents of matter. But the implications of Steinhardt's idea go far beyond the realm of particle physics. According to his theory, these cellular cosmos would be self-contained universes, each containing its own space, time, matter, and laws of physics. This means that there could be an infinite number of universes existing independently of our own. Each of these universes would be a complete and self-sufficient reality, untouched by the events occurring in the other. It's a concept that challenges the very notion of our universe as we understand it. So, what's the significance of this idea? Why should we care about the potential existence of infinite parallel universes? Well, for starters, it could help us solve some of the biggest mysteries of our universe. For example, one of the most perplexing problems in cosmology is the horizon problem. This refers to the fact that distant regions of the universe appear to be in thermal equilibrium, despite being causally disconnected. In other words, there is no way for these regions to have communicated with each other, yet they have the same temperature. According to the standard model of cosmology, this should not be possible. One way around this problem is to hypothesize that our universe is just one of many, and in other universes, conditions are very different. In this scenario, the apparent flatness and uniformity of our universe would be nothing more than a coincidence. By introducing the idea of a cellular cosmos, we can avoid this contrived explanation, and instead have a universe that is fundamentally self-similar. Another advantage of Steinhardt's idea is that it could help us understand the origin of our universe. One of the biggest challenges facing the theory of the Big Bang is explaining how matter came to be distributed in the early universe. According to the Big Bang theory, the early universe should have been a hot, dense soup of particles that were evenly distributed. However, this prediction does not match what we observe in the universe today. With a cellular cosmos, we can avoid this issue altogether, as the distribution of matter in each cell would be determined by the particular physical laws that govern that cell. Overall, Steinhardt's idea of a cellular cosmos is a bold and ambitious one. It offers a potential solution to some of the biggest mysteries facing modern cosmology. Whether or not the idea is ultimately correct, it serves as a reminder that the universe is full of surprises and that our understanding of it is constantly evolving. As we continue to explore the mysteries of the cosmos, who knows what other groundbreaking ideas we will uncover? If you found this video interesting, please like and share it with your friends. If you want to learn more about similar topics, you can check out the next video. Thank you for watching.